1 minute behind schedule, and I think we would like to keep that going. So I'll just share my slides here. Also, I'd like to take a moment to thank Nicola and everyone else who has been working tirelessly and always cheerfully behind the scenes to get this event together. And I think it's an amazing job, and everything is running smoothly, and I can say that because I don't believe in touch wood. So there we are. So we've seen an initial lab. I have 45 minutes to talk about and show you through the lab-based examples, MONAI for PyTorch users. So I have very few slides. Those of you who don't like code in the slides would be glad to know there is no code in my slides. And really the goal is to get to the notebook as quick as possible so you can continue to tinker. And this time we'll be tinkering with an end-to-end network, which does everything from fetching the data to creating the data sets, to instantiating the networks and running a training validation loop and looking at some visualization. But what I really want to talk to you about, because this is relevant to you, whether you come from a PyTorch background or whether you come from another framework, that there is a MONAI design philosophy that we've adhered to that is very much centered around PyTorch and what we think of PyTorch. Because obviously when building a new medical imaging focused deep learning library, there are a lot of underlying deep learning libraries that one could choose, and we have chosen PyTorch. And I think the reason for this is that many of us have been on our deep learning journeys through several frameworks, and it's been a common experience amongst a lot of the developers at KCL, certainly, researchers, sorry, at KCL, that I think we all find PyTorch a very nice library to work with. It has the nice combination of ease of use and sufficiently fine granularity that you can do arbitrarily powerful things with it. And so we adopted PyTorch as our underlying library, but we also adopted the PyTorch design and the PyTorch design philosophy, which is why MONAI, as you'll see, well, as you have seen and as you'll continue to see, looks an awful lot like PyTorch. And these are our key principles that we've really focused on, that MONAI continues to look like PyTorch, that it's opt-in and incremental, that it's collaborative in terms of the overall ecosystem that exists around PyTorch. And, well, yes. And it's actually becoming part of the official ecosystem of PyTorch, which is very exciting. So MONAI looks like PyTorch, as I've said, because PyTorch is a very successful framework. I didn't put graphs in the slides, but I did do a little bit of digging. Archive mentions of PyTorch are up 194% 2018 to 2019 versus TensorFlow up 23%. In major conferences, the survey of 9 major conferences, PyTorch had swapped over to become the most mentioned framework in 2 of them, was the most mentioned framework in 6 of them, and was closing in on the final one. So PyTorch is being successful, and one of the reasons is due to its pleasant design and ease of use. So we don't want to write a framework that throws that ease of use away, so we're not reinventing that wheel. And our principle has been that everything that we provide in MONAI is available in a vanilla PyTorch form, which is to say that for the most part, we try to think, how would a PyTorch developer write this particular piece of functionality? That's how we write this piece of functionality. And where we break from that rule, it's largely to do additive things. So as you've seen in Eric's slides, the MONAI transforms look like normal transforms, but they also have the capability of providing extra determinism in case you need it. And we really do think that determinism is a big feature of MONAI. So we go above and beyond what is natively provided by many transforms, not all of them, other transform libraries do this as well, but we found that it's a very useful thing to do, and it's additive, and it doesn't change the way you have to write your network, as you'll see. We also provide many wrappers to use with Ignite, because Ignite has also been adopted as an official PyTorch. I'm not quite sure what the term is, whether it's a component of PyTorch or whether it's strongly affiliated with PyTorch, but it is mentioned on the PyTorch site. And we write helpers that build on the Ignite API, so that if you like Ignite and if you want to use Ignite, you can use MONAI Ignite style, but all of the MONAI Ignite style bits and pieces will ultimately call the vanilla PyTorch bits and pieces that we've written for MONAI. So I say MONAI is opt-in. So basically that means that you can start off using as little of MONAI as you like. And we try to make it so that you never suddenly hit a cliff edge where we require you to rewrite your entire network to have access to one new feature. And this is very important. This is, again, something that we're going to continue to try to go with, because we think it's one of the key elements of making MONAI adoptable by everybody who wants to use it. So you can incrementally start using the parts of MONAI that you want to use. Obviously, transforms, as you've seen, is a big part of that. Medical imaging requires something of its transforms that you don't get with vanilla image processing. So we've worked hard to provide useful transforms, but also networks and training loops and metrics and all of those other things. You can start to bring those in as and when you want. So if you've written a PyTorch library and you need some help from MONAI, you can get it without rewriting your code base. But hopefully the next time you decide to start a new network, you may do it with MONAI from the ground up. So MONAI is collaborative, and what we mean by this is that there is a really nice ecosystem for medical imaging around PyTorch, and we don't want you to not be able to use it just because you're using MONAI. And I mean, this is transforms and networks and losses, but really the focus at the moment is on transforms. There's lots of transform libraries: Batch Generator, Torch.io, Phoenix Rising, ITK, NVIDIA, and they are designed in some cases with different philosophies as with respect to their API. And one of the things that we cared about early on is making sure that if you need one transform from library A and one transform from library B, we provide you the means of connecting those together. And we are PyTorch ecosystem friendly. Another thing that PyTorch has a lot of are quality of life libraries. And to name a few of them, we have Ignite, Lightning, Catalyst. We've adopted Ignite very closely because we find Ignite to be what I would call an unopinionated quality of life library, which isn't to say the other ones aren't. It's the one that we looked at early on. We decided it very much fitted our needs. And we wrap, as I said, many of our components in an Ignite compatible API. We are friendly with other libraries. You can see, for example, Lightning examples in MONAI tutorials if you're curious to see how you can interop with Lightning and Catalyst and some of the other libraries. And this is the reason this is possible is because we provide everything as vanilla PyTorch style components. So that's enough talking from me. The example lab that we have coming up is worth 1,000 words. What we're going to do is we're going to walk through this end-to-end classification example, downloading the data set, building a transform pipeline, and we're going to look at the journey from a vanilla PyTorch training and validation loop to starting to adopt Ignite. And you can see how PyTorch and Ignite and MONAI interact very happily together, coexist very happily together, and you never have to rewrite half of your code base. So let's jump straight to that. Oh, well, before we do that, we can have a very brief Q&A session if anyone has a burning question or two.
So maybe, Ben, maybe we can start with the notebooks and then we can collect the most common questions in the Slack channel and answer them when we summarize the notebook.
So we're looking at Lab 2, end-to-end model training and validation with PyTorch, Ignite, and MONAI. Just to say a couple of things about this before you get going. So we want you to play with this notebook and experiment with it. There's a few little things that we've thrown into it as activities, but we provide essentially all the code that you need to do anything that you want to do. So once you've worked through the basic network, have a look at the make some improvements sections. As I say, we have an Ignite training loop as well as a vanilla PyTorch training loop. There are still some problems about reproducibility, given that we're working with a Jupyter notebook. And one of the things that you have to be careful with is when you are operating a Jupyter notebook, if you are using any of the implicit NumPy random state calls, by running one cell in your notebook 0 or 1 or 2 times, you can end up changing and reducing the determinism in your notebook. So we'll ask you to take a look at the way you can sort that out. Part of it is through making use of some of the nice features of the MONAI transforms, and some of it is actually going through cells and making sure you create your own random state instances. That's all I have to say for now.
Okay, then by now everybody should have access to the notebooks and can get started. So I would suggest to do that, and we'll keep an eye on the Slack channel and we'll try to answer a couple of questions on the fly, and we'll go through the notebook together in a couple of minutes. I'll ping you in the main channel.
Okay, so I won't spend too long on this section. We've got some prerequisites that we need to run the network and visualize some results. We've got the torch import and MONAI imports of various types, and we just print a config just to be useful. Again, nothing particularly much to see here. So I'll just skip over those unless people have any burning questions that you should flag up in help notebooks if I'm going too fast. Set determinism. This is the first interesting part. So essentially what we're doing here is we are ensuring as much determinism as we can, given that we are still making use of the implicit NumPy random state instance for some things. So set determinism, what it does is it will set some of the GPU flags to slow the GPU down a bit in favor of numerical stability and reproducibility, particularly with parallelism, issues with numerical stability due to parallelism. And it sets a bunch of stuff for the CPU random state instance as well. However, we still have to be careful. As we'll see, there are a few places in this notebook where we call random state. And because the default use of most transforms, including the MONAI ones, is that they will use the global random state instance. If we start, because we're using a notepad, if we start clicking on things, we're going to change the way the network actually runs. For example, if we run this cell multiple times. So what we really want to focus on here, I think, is the MONAI specific stuff. So here are some MONAI transforms. Here is the compose pipeline. We're using the MONAI compose pipeline here. I don't think we actually need to use the MONAI one specifically, but Wenqi will talk to you about some of the nice features it has in his upcoming lab. And we just put this together. Again, there's not very much to see here. Essentially, the training transforms add the augmentation and the through rotates and flips and zooms, and the validation transform doesn't. So we create this simple derived data set. There's not much to this. Again, in general, you'll have your channels that you wish to work with, and you'll pass in your transforms. And essentially, you just have to look a little bit like an array in order to fulfill all of the obligations of Torch Utils data set. So down here is where we start doing heavy lifting. We have a thing that's known as the torch device. So here we're saying we want to use the GPU, and it returns us a magical thing which allows us to send things to the GPU. So we create our DenseNet instance. One of the people in the chat asked earlier, where does the size of the image come from? How does the network know about it? The answer there is the network will get it from the tensor at the point that it's actually being executed in its forward passes. We're going to use a cross entropy loss, and we use the Atom optimizer because it's an optimizer of good first resort. So here I exploded everything out so that you can see every step that's involved in a vanilla training loop. We've got our outer loop, which covers our epochs, and we have then to tell the network you are in training mode, and that will, depending on the network, optionally enable some elements which are used in training, such as normalization and dropout. We then fetch the inputs and the labels for each of the batches. We defined the batch size up when we defined the data sets. We zero the gradients for this particular step. You will not always want to do this if you want to start doing far more interesting multi-step training loops. You may not always zero your gradients, but for a vanilla training loop like this, you want to zero your gradients at the start of each step. We run the inputs into the net, we get the outputs, we pass them to the loss function, and then backward computes the gradients for us and optimize a step, because it has been passed the necessary bits and pieces, can then perform the update of the weights based on the backward pass. And really, that's all there is to a PyTorch training loop. So when we want to run the evaluation step, which we do at the end of each epoch, we switch off the training features on the network. We tell Torch that for the scope of this particular context, we don't want any gradient calculations, and we just basically run through all of our validation batches. We gather up the losses, and also we compute some metrics as well, some additional metrics, such as the receiver operating characteristic area under curve. And we use that to determine whether our network is or our set of weights is the new best set of weights. And if it is the new best set of weights, we let anybody who's looking at the output know about that, and we save that out so that we can use it later. I'll just get rid of those outputs. So we do a bit of light plotting of analytics. I don't really think I need to talk through those. That's all kind of, it's not even deep learning specific. But what I would like to talk about here is, particularly before I just touch on this, is I'd like to talk about how one makes a notebook like this deterministic. Because not everyone cares about determinism, but when you do, say, for example, you are exploring changes to individual aspects of a network architecture, or you are exploring individual changes to hyperparameters, being able to run exactly the same network with exactly the same starting values is very important. And so we can make sure that, for example, in our transformations, that we always get the same ordering of random rotates and flips and zooms. And we do this by setting random state on these transforms. These are MONAI transforms. And MONAI does allow you to basically say, for each of these individual instances, we want it to have its own random number generator, so it can't be affected by the NumPy internal kind of global random number generator instance. The other thing that I wanted to point out here is if you've run, let me just scroll up to this. Sorry for any scroll-induced dizziness. If you've run this multiple times, you'll see that each time you run it, we get a different number of images. And that's because we just said there is a 0.1 chance that an image is added to the validation list, and a 0.1 chance that it's added to the test list, and then a 1 minus those 2.1's 0.8 chance that it's added to the training list. And every single time we execute that, actually, you'll get a different number of images. Now, if we want to partition that more stably, we can just do something here where we say, well, okay, let's work out the validation count, given that we want 0.1 of our total images to be in the validation set, and same for the test count. And then we create an array with the appropriate number of zeros, ones, and twos in it, and we use shuffle. And shuffle will reorder those, and then we just go through, and for each image, we say append it to the appropriate group, depending on whether it's a test image or a validation image or a training image. And this way we can ensure that we have the same number of images. This kind of thing, there's probably libraries out there that give you standardized versions of these things, but if you want to roll your own with PyTorch and with MONAI, you always can. So finally, just to have a little look at the Ignite-based training loop. So Ignite provides you, as I said, it's very much of a quality of life library. So it's very good when you're getting used to a library to roll your own things and understand how everything works under the hood, because it means you are less likely to be surprised when things go wrong. But you only want to do that so many times. And a lot of clever people have spent a lot of time thinking about how to implement these quality of life utilities that you can bring into your own networks and models. And so Ignite provides us with a lot of standardized training and validation loops, and it provides us with useful functionality to avoid what is otherwise essentially the same kind of boilerplate that you tend to write time after time. So here we create a standard Ignite, a supervised trainer. There is also a MONAI supervised trainer, which builds on top of it if you choose to use it. And for validation, we create a supervised evaluator. And again, this is the Ignite supervised evaluator. You could use the MONAI one if you wanted to. And if you continue to play with this notebook subsequently, which I encourage you to do, you can try out all these different things, and you'll see they should all basically give you the same ability to train the model at the end of the day, just with less code. So what we do with trainers is we set everything up, and then we just let them run. And as they're running, they go through their standard training loop, and they emit events. And we can use decorator methods to attach functions to those events, which get called when we want them to be called. So for example, in the training loop for epoch completed, we run the validation, actually before we touch that. So for each iteration that's completed, we have a function that does the stuff that we want it to do when we end the iteration. So we want to get our loss, we want to look at the batch that we just got for that particular step. We can get the epoch out, we can find out how many epochs there are, and we can basically be as sophisticated as we like about what we output from our network at each iteration. So for example, here, if we scroll down to run validation, sorry, before we do that, I record both the losses for each iteration and the batch size, because unless you have an exact multiple of your batch size in terms of images, your last batch will be smaller, depending on how you set up your data set. And you can end up weighting that wrongly when you mean things. So by recording the batch sizes along with the losses, down here we can just use the nice NumPy weighted mean by adding our batch sizes as weights to the losses, and then we get our properly accurate overall average loss. So we're making use of some other useful MONAI, Ignite and MONAI features. So we can, for example, let me just find where it is in the code. Here we go. Can anyone see? Oh, yes. So the validation metrics here, we just created dictionary validation metrics. We want accuracy and we want receiver operating characteristic area under curve. And we assign those to a dictionary. We can pass them to the evaluator and say, hey, evaluator, please run these metrics. Now, this ROC AUC is an ignite wrapper for this compute rock AUC function that we see up here. So as I say, everything is available as vanilla PyTorch, and where it's useful for us to do so, it also is wrapped for Ignite. For us to finish on time, are there any final questions that people have about this notebook, comments, anything that would like to get off our chest before we move on? Anybody? Nobody? Okay, I think in that case, we can continue on time.